Okay, okay. This is figure 2.45. Problem number is 219, and it is 1 degree of freedom. And I have defined an angle theta over here. Angle theta, which shows this. Then I'm going to draw a free body diagram. So you have these pin forces that I don't bother to label because I'm not going to sum forces. I'm only going to sum moments. Then I have a spring force. So step 1 is to draw the spring force in. Step 2 is to write the formula. And so here's the formula for the spring force. It's spring constant times the deformation. The deformation would be L sine of theta because there's actually a little triangle here. And so it'll be L is the length along the rod. Sine of theta would be the distance, the vertical distance here, but because we're doing small angles, sine of theta becomes theta, so that's the spring force. And then to get the arrowhead, I imagine that theta is positive, so that it has rotated counterclockwise as shown. If that is what happens, then the spring is compressed or pushed. So if the spring is pushed, the spring pushes back, and so therefore the spring, the arrowhead goes down, as shown. Then at the end of the rod, there's also a damper. So I draw the line for the damper. Then I put a formula in for the damping force, which would be C 2L times theta dot. And then I imagine that theta dot is positive, which means that the rod is rotating counterclockwise. If it's rotating counterclockwise, it's pulling on the damper, and the damper then pulls back. So the arrowhead is down because it's pulling. The last force that is here is the spring, so I draw a line. I write the formula for the force. And then I imagine again that theta is positive. If it's positive, it's rotated in the direction shown. If it's in that direction, the spring is being pushed. If it's pushed, the spring pushes back, and so the arrowhead is also down. If I'm going to draw going to use transfer functions, so let's imagine that I am, then I need to excite it with some sort of a force or something. So take your pick. You can put it anywhere you want. I think what I'll do is I'll just for kicks, I'm going to say, okay, I'm going to twist it back here like I had a motor or something. I'm going to call it T for torque. I'm going to apply that. That'll be my input. That's what I'm going to use to excite it. Okay, so now I'm going to write the equations. The equations will be the summation of moments around the end. And so I have 3 forces and a torque. So let me put that torque in here. I'm going to say T. And then this term comes from this force. L is the moment arm. It's actually L cosine theta, which becomes just L. And it's negative because it's a negative moment. And then you have the other 2 forces, one here, which comes down to this term. And this is your moment arm. And then this term right here is the same as that one. So anyway, that's the summation of moments, and that's equal to J theta double dot. In this particular case, if you say that you want to find the J's, I'm not really focusing the class on that. You have 2 masses. You have a rod mass, which is, it's the endpoint mass, and that's the moment of inertia of a concentrated mass at the end of a rod, which is 2L long. That comes out of the textbook. I think your book has it as well. And then this term here is coming from the rod's mass, and that would be the equation for the moment of inertia at the end of a uniform rod of mass m. So anyway, that's the equations. You have one unknown and you have one equation. It's 1 degree of freedom, so everything seems to be working out just fine. What I did this time was I did not use the transfer function approach. I just, since it's a one equation with with a second order, I just took that and put it into the standard form. The standard form is this term here. This term here should be 1 for the standard form. So what I'm going to do is I'm going to take all of these and I'm going to divide by j. And so this term is here. Let me put it in a different color. This term right here is always omega n squared divided by j. So that term comes down here. So this the two blue terms divided by j, that is always omega n squared when you have a single equation with one variable with a 2 dots. The middle term here, and of course I have to divide by j, but this middle term, probably ought to do that in a different color. Middle term is this one right here divided by j, and that's always equal to 2z omega n. So you can find your z and your omega n or whatever. You can also do it with Mathematica, so we'll do that. Let's see, go up to Mathematica and let's see if I can open it. There we go. We'll do a new document. Quit. Let me enlarge it a little bit so it's easier to see. And then let's just type in this equation over here. Of course, I left off, I forgot again, my t right here. This guy has to come down here. Boom, down here, which is going to be a t right there. Okay, so I'm just going to type in the first one up there into my Mathematica. So I only have one equation. So the equation is, I don't need a brace because I've got everything. So it's t minus k1 l theta. I'm going to say th for theta times l minus k2 times 2 times l times theta tl. Get this guy out of the way. K2, 2L, theta times 2 times L minus C times 2 times L times theta times S times 2 times L equals J S theta. So that's my equation. And I want to solve the equation for theta. And there you have it. Let's shrink this guy down and make this one big. And I should probably just copy and paste. There we go. Copy. And we'll say, okay, transfer function. It's not exactly the transfer function because it has the input in there. But there you go. T is the input. We can do whatever you want to with this. So for example, let's put in some numbers. So K1, K1, we'll let that be 1. K2 is 2. C, we'll give it a little bit of damping. L, we'll take that to be 1. And J, we'll give it a 4. Alright, so boom, and then we'll take a look at the transfer function. There we go, not too bad. All right, let's find the, take the denominator, so we'll take the denominator of the transfer function, set it equal to 0, solve it for s. So we'll go back over here to say solve for s, and so it wants to oscillate. The frequency is about 1.5 radians per second. The time constant is going to be 1 divided by 0.05. So you can figure out all that. It's stable, et cetera, et cetera. Let's go in and find the steady state response, steady state angle when the torque is equal to, let's say, constant of 10. So we'll say, okay, I need to, step 1 is to solve for the output theta. I have that. That's what the TF is. All right, so I've got that. Let me just copy and paste it. Okay, so we'll copy, bang, bang, bang. There we go. I put in step 2, I put in the Laplace transform of the input. So if it's a constant of, I think I said 10, so it would be 10 divided by s. Step, was it 3, is to multiply by s. So I multiply by s. Step 4 is to take a limit. So we'll just come back over here and we'll say limit this as s. I say minus, I say greater than 0. And bang. So if you apply a torque of 10, whatever the units are, meter, Newton meters, or whatever your units are, if you apply 10, you're going to get an angle of 1.1 radians. Let's go in and find the steady state amplitude for a sine. So let's start with the transfer function. There we go. Let's say that the input is, let's say 20 times the sine of 2t. All right, so 2 is the forcing frequency. So what I do is I replace s with 20 times the imaginary number. Did I say 20t? I don't know what I said. Okay, it'll be magnitude. We'll let the magnitude of t be 10 like we did before, so t is 10. Sine of 20 time. So we'll do this, and we come up that's too small. Let's get something serious. Okay, so we'll say frequency is 2, amplitude is 10. There we go. Those are more reasonable numbers. Okay, so we want the amplitude, so that's the absolute value. Let's see, did I give this guy a name? No, but I can say absolute. Let's name it something. Okay, so we'll say this is at 2 radian per second. This is what it is at 2 radians per second. I'll put a parentheses around there just to, okay, so what's the absolute value at 2 radians per second? That's the magnitude. All right, so that's how much the angle will oscillate. If you want the angle, I want the arctan, and remember it has to be the real part first and then the imaginary part. Okay, so this would be minus 1.41 and minus 0.161. And this always comes back in radians. I don't like radians, so I'm going to take degree. Bang. So it's negative 173 degrees is the phase angle. Okay. So I think I've done just about everything that you might want for this. So I will